morning. We begin lecture 36. In today's lecture, we'll be covering the first space-time code that has been proposed in 1998, that is referred to as the Alamouti code. We'll also talk about the channel state information, the different forms and how it plays a role. And this will build up our understanding to start beginning our discussion on channel capacity. So the channel capacity is the next unit that we are addressing. A very good reference for that will be Goldsmith chapter 4. I would very much encourage everyone to read this, because this material is not there in some of the other references. So therefore, this is a good place to begin. But to summarize yesterday's discussion, there were two key concepts that we introduced. That one was the understanding of the benefit of diversity being split into two components. One is the array gain, the other one is the diversity gain. The array gain defined as the average SNR with diversity divided by the average SNR of a single antenna. So in the case of the MRC, we got a value of M. It turns out that's the maximum that you can get in terms of array gain. If you have M elements, you can get an array factor of M. And that's, for example, the benefit that you would get in terms of the improvement in SNR. The diversity gain, by the way, array gain comes whether there is fading or not. The diversity gain comes in primarily when there is fading, because you're trying to improve or change the statistics of the fading distribution. So array gain and diversity gain, probably the best way to remember it is the graph that we have drawn yesterday. So I would like you to review that once more. This is the bit error rate of any modulation scheme in AWGN. The performance in a single antenna channel, we can even mark it down as n equal to 1. Single antenna. Now, if I move to n equal to 2, I saw a different slope. That difference between the two performances, we have split up into the array gain, which will be a factor of 3 dB because of the second antenna being optimally combined. Again, it may be less than 3 dB if you have done not maximal ratio combining, but you have done equal gain combining, for example. So this shift, you should not always mark it as 3 dB. It's the shift that you get is because some array gain that you have obtained. If you've gotten 3 dB, that's the best that you can achieve. So therefore, you're doing something in terms of the optimal performance. Now, what is the balance is over and above the array gain is the benefit called, as we refer to as the diversity gain. The combination of the two is the net benefit. So therefore, when you think about it in terms of the net improvement in performance, we don't say, oh, I got so much BR improvement due to array gain, so much. No. It's more of a intuitive understanding saying, maximize your array gain. Then you will see that the maximum overall benefit you have maximized as well. And the diversity gain is something that will show up when the fading is severe, and therefore you will get a significant improvement in terms of the performance. So the way to summarize would be is the total benefit. The total diversity benefit is a will be a combination of the array gain in dB, because if it's in linear scale, it will be a product of the two gains. Because it's in dB, it's an addition of the two gains plus what we get as the diversity gain. And we mentioned in the last class that things that can reduce the diversity gain are weak antennas, correlated antennas. You did not implement maximal ratio combining. So several things that could reduce the benefit of diversity gain. Some of those could even reduce the benefit on the other side as well. But important thing is to know that it's a combination of these two systems that we are working with, and this is what we would like to maximize. The other important result that we discussed in the last class was numerical integration. Again, just as a quick refresher of what we have talked about in the last lecture, Q of Z normally defined as the complementary error function which is given by 1 over root 2 pi integral z to infinity e power minus x squared by 2 dx. Now this form is very convenient for several of the integration problems that we encounter, but if you want to do numerical integration, two things: one is the limits are infinite, the other one is it's dependent on the integrand itself. So an alternate expression for q of z, which we said would be more useful from a numerical integration point of view, was 1 over pi integral 0 to pi over 2 e power minus z squared by 2 sine squared phi d phi. Okay. So that would be our equivalent expression that we want to leverage. Now we said that the probability of BPSK is one where you would have the Q function, and likewise there are several modulation schemes. In fact, most of the QAM modulation, 16 QAM, 32 QAM, all of those will have a Q function as part of the expression for error. So any of the general family can be handled in the following fashion. As an illustrative example, we took BPSK. Probability of error of BPSK in fading. This would come out, the basic expression would be integral 0 to infinity q of root 2 gamma. You can take any q, any function, any function of the BR which involves q, we could do the same method, f gamma of gamma d gamma, and we showed that once you substitute the new form for the q function, this can be written as 1 over pi integral 0 to pi by 2 psi of gamma, that's your moment generating function, evaluated at minus 1 by sine squared phi d phi. Okay. Moment generating function we assume is known, that can easily be programmed. So you basically feed in different values of phi, compute the argument minus 1 by sine squared phi, compute the moment generating function, and then perform the numerical integration. So the integrand is well defined, the integral is well defined, so therefore it's easy for us to work with. Okay. And as a special case, we said for M branch MRC combining, this particular expression would be 1 by pi, special case for would be 1 by pi integral 0 through pi by 2, 1 divided by 1 plus gamma by sine squared phi raised to the power m d phi. Okay, where gamma is your average SNR that is provided for us. Again, this is in terms of the numerical integration. Once you're given gamma, once you're given m, this should be something that we can readily program. And special case of the special case, if you take m equal to 1, you basically get single antenna Rayleigh fading. Single antenna Rayleigh fading, and you can verify that you're getting the forms that we are interested in. Okay, so that was primarily the key concepts that we developed in the last lecture. Now, we also talked about channel state information. I want you to start thinking about channel state information in the following manner. So, if I have a transmitter and my transmitter has many antennas, so let me say that it has got NT antennas. So this is my transmitter, NT antennas, okay, and I have a receiver which has NR antennas. This is the most general type of situation that we will encounter. NR antennas. Okay, this is NT transmit antennas, NR receive antennas at the receiver. Let us take the simple case of flat Rayleigh fading channels. Rayleigh fading. Okay. Now, describe for me what is the channel between the transmitter and receiver. How would you characterize the flat fading? Means it's between every transmit antenna, every receive antenna, it is a single Rayleigh fading coefficient. Okay. Now, there are NT signals that are getting transmitted. Each of those NT signals will be picked up by each of the NR antennas. So, this channel that is in between here is a matrix channel, okay, because it connects NT transmit antennas to NR receive antennas. So, if I were to write it in matrix form, the transmitted signal from the different NT antennas would be S1, S2 dot 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 S of NT, and I would pick up on NR received signals R1 to RNR. So, NT inputs, NR outputs. So, my matrix is a NR cross NT matrix, where each of these coefficients, let me call this as Z11, Z12, Z1 comma NT. What is the definition of that? That is the channel between the Zij is from the jth transmit antenna to the ith receive antenna. So, basically all of these coefficients are the ones that will contribute to R1. Similarly, there will be Z21 to Z2 comma NT. Okay. Again, this is notation that will be very helpful for us to visualize. Okay. And the last of these will be ZNR comma 1, ZNR comma 2 dot 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 ZNR comma NT. Okay. So, keep in mind that this is the channel that if it is a flat fading channel. Okay. Now, if I were to ask you single transmitter, single receiver, CISO channel, what does your matrix look like? 1 cross 1. Okay. So, basically it collapsed in both dimensions to become a 1 cross 1 system. So, if I were to tell you I have 1 transmit antenna, 2 receive antennas, this becomes a 2 cross 1 matrix. If I tell you that is receive diversity, if I tell you it is a transmit diversity system, 2 transmit, 1 receive, it will be 1 cross 2 matrix is what represents the channel. Okay. So, all special cases, all combinations, CISO, MISO, CIMO, MIMO, all of them can be covered by once you understand this basic picture. Okay, good. Now, just to make it a little bit more interesting and challenging, what would happen if this were a time dispersive channel? What would happen if it's a time dispersive channel? Let's say that it's a discrete channel that is between the transmitter and receiver. So, in a CISO case, if it was just a flat fading channel, you would represent it by some coefficient Z1. Now, if it was a basically it's a time dispersive channel, then it becomes Z1, and then there is a Z2 with a different delay. Maybe there are some number of taps that are present in the system. So, if you were to represent this as a filter, H of Z, Z is not basically if you were to represent this as a filter, let me just denote it in DSP terminology. If I were to denote it as a filter, I'll call this as some H of Z. Okay. It's got some impulse response and it's got a response. So, what would happen in this if this became a MIMO system with time dispersion, then each of these from being a single coefficient will become a polynomial, become H11 of Z. Okay. Each of them becomes a polynomial. So, it becomes a polynomial matrix. Okay. But we will not complicate things today, we will just treat it as a flat fading channel, which means it is at any given time if you take a snapshot, it will be an NR cross NT matrix with NR times NT Rayleigh random variables, each of them are independent of each other, that is present in the system. Okay. Now, given this framework, I would like you to follow along in this fashion. The whole notion of CSI. CSI channel state information means you know this Z matrix. That is all it means. That means that part of it is known. So, now the following are important. let us take the case where you have an FDD system. Always to visualize, think of it as a base station and a mobile. The downlink and the uplink are on different frequencies, F1 and F2. Because they are on different frequencies, the channels seen in the uplink and downlink are different. So when I look at the information, I am not going to worry about F2 for the moment. I am going to remove F2 from the picture. Okay, keep in mind that the uplink is a different frequency. Now, channel state information is an understanding of what is happening in the channel at this frequency F1. Okay? So, CSI at this frequency F1 is happening in the channel. Now, what happens when my receiver receives the signal? So, at the receiver, I try to estimate the channel. So, then what I get is CSIR. I have estimated the channel state information at the receiver. Now, does the transmitter know what the channel state is? Absolutely no idea. It has no clue, because F1 is, it only sees F2. So, it knows channel state information at F2, but it does not know channel state information at F1. So, the only way that the transmitter is going to know what the channel state information is if the receiver passes that information. Okay. So, this then becomes, maybe to clarify, this is CSIR at F1, the downlink frequency, and what was fed to the transmitter was the channel state information also for frequency F1, but it was now the information is available at the transmitter. So, this is the setup that we have for feeding back the information. So, what information does the transmitter need to know? It needs to know what was the channel experienced by the signal when it transmitted. So, that information can only be given by the receiver on the feedback path. Okay. So, we can write down the following: CSIR is channel state information estimated by the receiver. Estimated by the receiver. Okay. CSIT. There are two cases. One, when CSIR is fed back by Rx to Tx, and this is true for FDD systems. What's the difference? Now comes the TDD case. TDD case, I have the transmitter, I have the receiver. TDD system, there is only one frequency that is going between transmitter and receiver. Okay? Both are transmitting. So, when the mobile transmits, the base station already knows what is the channel state information of F3. So, in the case of TDD, that is the second scenario, CSIT is actually estimated by the transmitter itself. So, CSI estimated by the transmitter itself. Okay. So, this is for the case of TDD. Is it clear why TDD is different from FDD, why CSI has to be fed back in one case and in the other case it does not need to be fed back? Is that clear? What is the assumption that you have made? That TDD transmission is reciprocal. What the base station sees channel is the same as what the mobile sees, and to a very large extent that is, so we can also maybe make a comment that you have assumed TDD channel reciprocity, which is a fairly good assumption. There is nothing wrong in that, channel reciprocity. Okay. So, in a nutshell, what are we trying to do? We want the transmitter to know what is the channel to which it is transmitting. At the end of the day, that is the simple thing. The reason for that is, if the transmitter knows it is a good channel, maybe it can send more information. If it knows it is a bad channel, maybe it sends less information or sends less important information, or introduces more error correction codes. See, that knowledge of how to transmit the information is very critical, and that is only possible if the transmitter knows what the channel conditions are. Okay. So, when you start now saying, I want to understand the capacity of the channel, capacity says what is the maximum information I can pass through the channel. So, then you start to think, okay, if my transmitter has no information what the channel is, it could be very good channel or very bad channel because of fading. It has no idea. How will it design the system? It will design it for worst case. It will say, I don't know whether it's good or bad, so I will design it so that it will survive even the bad channel. But that means it's going to send only a limited amount of information. But if it knew in a dynamic fashion what is the current channel conditions, then it can optimize the rate. It will not transmit at a fixed rate, it will be adjusting the rate, and because it's able to adjust the rate, it will achieve better capacity. So CSIT is very, very important because that is what will help us achieve capacity. But that's the topic for our discussion today. But before that, let's first look at one of the space-time codes. This is a case where I have 2 transmit, 1 receive. Now I hope you'll know what the dimensions of the channel matrix are. So that's the Alamouti code. This is where we left off in the last lecture. So let me pick it up from here. 2 transmit antennas, each of which are transmitting different signals. They are experiencing different independent Rayleigh fading coefficients, Z1 and Z2. It looks like a problem situation because these 2 signals are going to interfere with each other. However, the algorithm that was proposed saying, okay, take Z1 star times R1 and Z2 times R2 star seems to have done something. We maybe already have gone through it and figured out what exactly is happening, but basically this is what we got as the output. So this is where we pick up our discussion today, and we write down the second of those 2 equations. So in the same manner as the previous one, so there we managed to get S1 out of the 2 equations. So if you do minus Z2 star times R1 plus Z1 times R2 conjugate, what you will find is that you will get mod Z1 squared plus mod Z2 squared times S2 conjugate plus 2 noise terms. Again, the noise terms are not important for us. All we will make a note is that the noise variance is going to increase by a factor of 2. Okay? So equation 1 gave us S1. So this gave us S1. So this helps us to detect S1. And equation 2 helps us detect S2. It helps you to detect S2 conjugate. It's trivial. Basically, you can get that means you can get S2 as well. But notice what is your channel coefficient. The channel coefficient is mod Z1 squared plus mod Z2 squared. Even if one of them is in a fade, you will still be able to get robust detection. So you have gotten diversity gain. Diversity gain is what helps you when one of the channels is under fading conditions. So this is a very important result, because what it says is typically we think of diversity as something you can get when you have multiple antennas at the receiver. What this technique said was, no, that's not necessary. You can actually transmit 2 signals from the transmit on the transmit side. Traditionally, what you would think, if I transmit 2 different signals on the same frequency, they will interfere with each other. I'll have a big mess at the receiver. But what this one says is, no, if you design your transmission carefully, then you actually get 2 branch diversity in this system. Okay? Everyone is very happy with this result. First question they will ask is, can I extend it to more? If I use 3 antennas, can I have 3 branch diversity, 4 branch diversity? So it turned out that this was not easy to generalize. So again, but let's understand what are some of the key benefits. Why was this such an important contribution to the field of communications? So first thing we always ask is, when you get something, is what is the price that I paid? Because there's a basic tenet which says you don't get anything for free. Somewhere there is a price. You have to. So what is the price that we pay? So here we said, okay, how many symbols did you actually transmit? 2 symbols in 2 time instants. Okay, 2 symbols transmitted over 2 symbol periods. So I did not compromise on the symbol rate, right? That's very, very important. Transmitted over 2 symbol periods. That's very important, because if I transmitted 2 symbols and I took 4 symbol periods, then I wasted bandwidth. So this is something which is an important. So over 2 symbol intervals. So I have not increased my bandwidth. I have not lost rate. So that's an important observation. There is no reduction in the information rate. Okay, that's an important one. But I obtained diversity gain. Okay, so where did it come from? Where did it come from? But diversity gain, yes, diversity gain is very much present. Okay, so we then go back and ask the question, okay, now where's the secret? What's happening? This turns out to be the insight and the power of space-time codes. So let's take a look at, so if you want to visualize it, this is what is happening. So the signal that was transmitted is the following. So let's draw it in an expanded form so that it will be easy for you to make the additional notations. Okay, so I'm going to mark time on this axis, time, and it's increasing from top to bottom. This is space. So whatever I'm writing on the first column is a symbol transmitted by antenna 1, transmitted symbol by antenna 2. So please fill in this matrix. So antenna 1 at time instant n equal to 1 transmitted S1, at time instant n equal to 2 transmitted S2. But on the other hand, antenna 2 transmitted minus S2 conjugate and transmitted S1 conjugate. So instead of just transmitting S1 and S2, you over a 2 symbol period, you seem to have transmitted a 2 cross 2 matrix. But it's very important to note that this matrix is not just any matrix, it's got a very important structure, which is the orthogonality structure. S times S Hermitian, or if you want to take S Hermitian times S, you will find is equal to mod S1 squared plus mod S2 squared times the diagonal matrix. Okay, it's got a very important structure. So it's a non-trivial structure. It's may not seem very obvious, but this is a very important form that we know in signal processing as a orthogonal matrix. So basically, if you take one as cosine, one as sine, and the other one as cosine, you'll find that it satisfies this type of a structure. Okay. Now, to do a little bit more linear algebra, because a lot of this insights become very handy. I want you to write down R1 and R2, the two signals that are received by the antenna, receive antenna. There's only one receive antenna at 2 instances of time. I want you to write it down in matrix form. And the matrix form representation is very useful and important for us. So R1, if you go back and look at it, I want you to write it down in terms of S1 and S2 conjugate. Okay, this turns out to be Z1 minus Z2. R1 is Z1 S1 minus Z2 S2 conjugate, which is what if you go back and look at it, plus eta 1. Okay. That is the first equation. The second equation, R2, basically we saw R2 conjugate, but you can write down R2 becomes equal to Z2 conjugate, Z1 conjugate, and S1 S2 conjugate, and this one becomes N2 conjugate. Let's put the within brackets. Okay, N2 conjugate. So please verify that the equations that we got are of this form. Notice that what we have constructed also is a matrix that has that orthogonality property built into it, because if you do Z Hermitian times Z, what you will get is mod Z1 squared plus mod Z2 squared into the identity matrix 1 0 0 1. So what did we actually do in the process of detection process? We took Z Hermitian and then multiplied it with the R matrix, okay, and we found that the equations that were of interest are, basically at one time instant you get S1, the next time instant you get S2, and you get the desired detection mechanism. So this is a very simple 2 cross 2 system where orthogonality was built into the transmission process, so that you could then detect the signal without any complicated signal processing, without having to do any interference cancellation. Basically, the orthogonality structure gave you the interference cancellation as part of the computation.
Sir,
Yeah.
first equation which we saw yesterday, sir.
Is it not? Let me just take a look at it. Z1 S1 minus Z2 S2 conjugate.
The second equation,
R2 is Z1 star. Oh, this should be a conjugate. Thank you. Yes. Is that correct, everything? Yes, it should be R2 conjugate. You are right. Because only then I'll get Z1 star, S2 star, Z2 conjugate, S1. Yes, correct. It's R2 star. That is correct. Okay, but the Z matrix is correct, and so I probably will have to work with. I'll have to check this equation, the receiver equation. I won't write this down, but basically the received signal is correct if you put a conjugate sign. Thank you for pointing that out. Okay, now I want us to analyze the system that we have designed. Okay. First of all, I want to understand what is the, basically I'm trying to get the signal to noise ratio. So I want to compute the SNR. Compute the SNR. Okay. So if this is the final form that we are getting, the form that we are getting is of the following structure, where let me just take one of the two equations. What we have is mod Z1 squared plus mod Z2 squared times S1 plus Z1 star eta of 1 plus Z2 eta conjugate of 2. Okay. Now, I want basically you get several equations. Now, what happens in time instances 3 and 4 in case so time instant 1 and 2, this is what we transmitted. So, antenna 1, antenna 2, time instant n equal to 1, n equal to 2. That's all we have specified so far. It was S1, S2 minus S2 conjugate, S1 conjugate. Okay. Repeat the same structure going into time n equal to, let me use a different color, n equal to 3, n equal to 4. This would be S3, S4 minus S4 conjugate, S3 conjugate. So you would detect two symbols at a time and basically get the benefit of diversity. It is not a symbol by symbol detection, but it is two symbols at a time. But basically every time you want to detect a symbol, your equation is of this form. This is the general form of the equation. So there is a signal term which is mod Z1 squared plus mod Z2 squared. Then there's Z1 conjugate times a noise term, Z2 conjugate times a noise term, and I want to now understand what is the signal component. Signal component will be mod Z1 squared plus mod Z2 squared. If I take it as a scaling of the amplitude of the signal, when it comes to energy or power, it will become square of that times whatever was the energy of the signal S1. So whatever was the signal energy, scale factor times the square of that. Okay. What is the noise component? Noise component, it is sigma n squared, that's the noise term, but because you multiplied it by mod Z1, I have to scale it by mod Z1 squared. The variance will go by the magnitude squared. And similarly, there's a second noise term, sigma n squared mod Z2 squared. That would be the effective noise variance. Okay. Now, one thing that we should not forget, what did we do? I transmitted from 2 antennas. So I must not forget this 1 by square root of 2, because that's what makes that I'm transmitting with the same total transmitted power. Okay, that don't just keep in mind that that factor of 2 should not be omitted. Okay, so now comes the computation of the so the effective SNR that we will. So by the way, so this should be ES by 2. ES is when you transmitted all the power through one antenna. This one would have an S1 by root 2 sitting there because you did the scale factor of root 2, and then when you actually compute, it will be ES by 2. So SNR will be the ratio of the signal component to the noise component, which comes out to be mod Z1 squared plus mod Z2 squared divided by 2, that's that by 2 factor ES divided by sigma n squared. So we have shown the following result, that it has diversity gain. Alamouti scheme is a transmit diversity scheme. It enables you to get the diversity gain without any complexity at all. Basically, you have to detect 2 symbols at a time, and you are able to get it with simple matrix manipulation. However, did you get array gain? So this is diversity gain, right? This is diversity gain. Diversity gain. If you had obtained 2 times ES by sigma n squared, then that would have been array gain as well. But definitely you did not get. There's no 2 in the numerator. It's basically, this looks like the SNR of a single antenna. So what is happening to array gain? So this is where I want you to think about array gain in a sort of an intuitive manner. So what did Alamouti scheme do? Like most transmit diversity schemes, it had to preserve the total transmit power. So that's why this 1 over root 2 is there. Okay? So the total transmit power that is entering the channel is constant. And how many antennas do we have? Only one antenna. Whatever I can intercept with one antenna is what I can benefit from the receiver. The total transmit power has not increased. So effectively, this looks like a seesaw channel, single input, single output system from a power point of view. Right? Because the total power coming in is the effective power of one antenna. What is getting used as the receiver is that of a single antenna. On the other hand, if I had received diversity, I have one transmitter, I have 2 receivers. Is this any different? From a diversity point of view, no, I still will only get 2 diversity channels, and if I get mod Z1 squared plus mod Z2 squared, diversity benefit is obtained. But notice, I transmitted with a certain amount of power, but I have 2 antennas that are listening to the signal. So that means I can pick up twice the amount of energy that I will pick up with a single antenna. So this is a 1 cross 2 system, so which basically implies 2 times the signal that I can pick up, signal that is intercepted or that is received. Intercepted is because your antenna is intercepting the maybe just write signal received. Okay, 2 times by a signal received by a single antenna, and that is why receive diversity gives you array gain as well, because there are more antennas picking up energy. It is picking up energy, so it gives you diverse array gain. Because there are uncorrelated antennas, it's also giving you diversity gain. But if you cannot afford, or complexity wise you cannot put the multiple antennas at the receiver, Alamouti scheme says no problem, I can do it for you at the transmitter, I can get you the diversity gain, but I cannot give you array gain. That's okay, that's fair enough, because I could not put in the multiple antennas, so therefore, okay. So a good statement to summarize would be RX diversity schemes. RX diversity schemes will have diversity gain, yes, they will have array gain, yes. Now how much array gain, how much diversity gain depends on which diversity scheme you have implemented. Okay. On the other hand, TX diversity schemes, because I have to conserve power, I have to do the scaling of the signals. This diversity gain, yes, array gain, no. Okay, only diversity gain, no problem. It's but still never in a fading channel, diversity gain is a huge advantage anyway. So therefore, we will take that as a a bonus. Okay, any questions? Topic that kind of emerges more or less in a very natural fashion from what we have been discussing so far. It's the topic of capacity of wireless channels. Okay. A quick quiz on capacity that you would have studied in digital communications. Contributed by Claude Shannon and the year 1948-49. What are the two papers? A mathematical theory of communication and communications in the presence of noise. Those are the two papers. Okay. What is, if you were to give me the channel capacity theorem, what is that? There is a number C below which you can transmit with almost zero probability of error, but complexity is not specified. It can be very, very complex system, but it, if you cross that capacity C, there is no way you can get low probability of bit error. Basically, you will get very high bit error rate. Okay, so very good. So the capacity, our notion of capacity is primarily from the context of AWGN channels. The understanding is that there is a capacity number C which represents the maximum data rate at which you can transmit, you can communicate reliably. Maximum rate that can be transmitted over a channel, over that particular channel, AWGN channel, transmitted over the channel, with asymptotically small BER, with asymptotically small BER. Okay, so almost zero BER. Okay. Now, given that, and of course, there is no guarantee, nothing has been mentioned, so there is no constraint on how much processing you would have to do and what delay it would cause. No constraint on delay or complexity. And this delay and complexity can be at both ends. It can be at encoder or it can be at decoder. These are, it's a very, very open-ended statement. All it says is you can communicate reliably. So always we are interested to know what is the capacity of a given channel. So we know from Shannon's channel capacity theorem, C is given by, it's proportional to bandwidth. B is the bandwidth of the channel, logarithm base 2 1 plus SNR. Okay, gamma is your SNR, and the units are bits per second. That's the capacity theorem. And very often we also look at C divided by B, capacity per unit bandwidth, and in that case it will become bits per second per hertz. And that's a good way to compare different systems, because one of them may be 30 kilohertz, another one may be 200 kilohertz. How do you compare the two? Look at the normalized capacity per unit bandwidth. Okay. So again, the derivation of the capacity involves two quantities. One of them is the entropy. So the derivation of capacity depends on the definition and understanding of entropy, and also how entropy is related to mutual information. Okay. I will assume that this part of it is familiar, that of course for us the key equation that we are interested in is what is the capacity number. Okay. So first and foremost, what is the impact of this capacity? I want you to have a intuitive feel for that. So let's take an example. examples always help us capture the importance of a particular concept. So the first thing is, supposing I were to give you, I want to translate Shannon's capacity from a theoretical concept into a very practical concept. Okay, I've set up a transmitter, I have a receiver, there's a certain distance between them, propagation loss, some SNR is received at the receiver. Okay, that's the scenario. So here it is, a very simplified model. The noise spectral density is 10 power minus 9 watts per hertz. The equivalent bandwidth of my system is 30 kilohertz. The combination of these two tells me that I know what my noise power is, because noise power is N naught into B equivalent into B equivalent, that is given, I multiply the two, minus comes out to be minus 45.23 dBW. That's my noise floor. Okay, that's my noise floor. Now we are told that that the propagation equation, that received signal at a distance d is given by basically the breakpoint model, Pt times d naught by d, the whole cubed, path loss exponent is 3, and we are given that the breakpoint is 10 meters and the transmit power is 1 watt. Okay. So now simple calculation, I want to know what is my SNR at d equal to 100 meters. I would expect that this would be something that you would be able to do very, very easily. So this would be equal to, first of all I need to compute the received signal power, PR at 100 meters, that would be 1 watt into 10 divided by 100 meters raised to the power 3, that if I convert into dB will be minus 30 dBW. So my SNR gamma 1 will be signal power minus the noise power, which will be minus 30 minus of minus 45.23, which is 15.23 dB. Okay. Up to this, nothing new. Basically go back to the propagation model, plugged in the values, obtained the SNR of the channel. Now comes the important one. Now if this is the channel that you have, what is the capacity of the channel? Okay. So then we say, oh, I can tell you that, not a problem, because capacity is equal to the bandwidth times logarithm base 2 1 plus SNR gamma 1. Okay. Log 2, we have to calculate everywhere log 2. So log x base 2 is the same as log x base 10 divided by log 2 base 10. Okay, please, if that's the easier way, make sure that, we have to calculate log base 2. So it will be 30 kilohertz logarithm of 2, 15.23. I have to convert it into a linear scale and then basically compute the logarithm base 2 of 1 plus gamma 1, and please verify that this comes out to be approximately 153 kilobits per second. Okay. Now why are we spending so much time on this? For the following simple reason. Supposing I moved my receiver to a distance of 1 kilometer, 1000 meters. Basically from 100 meters I moved it to 1000. I am transmitting with 1 watt, right? I am not transmitting with low power. So now calculate the capacity. So what you will find is that the received signal power is now less. It turns out to be minus 60 dBW. So which means my new SNR, let me call that as gamma 2, comes out to be minus 14.77 dB. It's actually negative now. So this new position is not a good one at all for me from a transmission point of view, but did the channel Shannon's capacity also indicate that? Yes, if you calculate C2 as 30,000 logarithm base 2 1 plus gamma 2, it comes out to be 30, when you use 30 kilohertz, what would you expect as the nominal rate of the symbol? At least 30,000 kilobits per kilobaud, right? And if you use 1 bit per second, 30 kilobits per second. Please note, it's 1.42 kbps as predicted by Shannon's capacity, and this too with infinite complexity. So why is this discussion very important? Because if somebody gave me this problem statement and said, hey, I know large scale propagation, I know channel models, I know how to calculate breakpoint model, no problem. I would have said, hey, no big deal. I can predict for you what is it, you want to transmit 20 kilobits per second, no problem. 1 kilometer. 1 kilometer, what is the capacity? It's 1.4 kilobits per second. Even if you do infinite complexity, you will not get any transmission, useful transmission. So this is why capacity is very important. We've been able to predict SNR. But we now need to know how much information can I transmit and how do I maximize that information that goes through. Why? Because this is only the average SNR. Remember, what is the scenario in Rayleigh fading? There's not a constant SNR. So if I were to ask you, what is the capacity of this fading channel, what will you say? Tell me what is the instantaneous SNR. Instantaneous SNR is gamma, average SNR is uppercase gamma. This is of no use at all for me in calculating capacity because SNR fluctuates. So in fact, a Rayleigh fading channel capacity, what is the capacity? High now, low now, high now, low now. That's the channel that you have. Now the problem statement is, get me the maximum capacity out of this channel. That's now we start to say, hey, I know how Rayleigh fading fluctuates. I know Shannon's capacity theorem, and then I say, now put these two together. Oh, now maximizing capacity in a wireless channel is not at all trivial. It's going to be something which is very dynamic. I must know how to work with this channel. So first of all, if it is a CISO channel, it's a tough problem. If I now say it's a CISO channel but with multiple antennas, basically it's a single user CISO channel. Okay, that's the simplest of the cases that we can deal with. That's what we will deal with first. Second complex, the difficult situation will be single user MIMO. If I allow the user to have multiple transmit, multiple receive, because already Alamouti showed us that you can you get a certain benefit from doing the MIMO system. And then of course the most complex, which will be in an advanced course, not in this one, will be multi-user MIMO. If you now have multiple users who are accessing the channel, and then you get the benefit. So what we will be focusing on is the single user CISO channel and single user MIMO channel, but that itself is a very interesting problem by itself. Okay? So that's what we will address in the course of next week and in the lectures to come. Thank you.